This is Dr. Hessel producing the second podcast on physics of anesthesia machine. This is an outline of the material that are included in this topic. I have underlined the three main topics that I will discuss during this podcast, as well as the two starred items. The rest of the items are to be found in the wiki of the complete PowerPoint on this topic. I have already discussed the reading assignments and the sources that I have used for generating this podcast. As an introduction, I think we should review what we mean by partial pressure. This is the pressure exerted by a particular gas in a mixture of gases. When only one gas is present, the partial pressure of that gas is the barometric pressure. When there is a mixture of gases, the partial pressure of a given gas is given by the barometric pressure times the concentration of the gas expressed as a fraction, i.e. the percent divided by 100. Dalton's law says that for a gas, the total pressure is simply the sum of all of the partial pressures added together. This, for an example, shows the content of gases in room air. Total barometric pressure is about 760 millimeters of mercury. Air is about 77% nitrogen for 585 millimeters, 21% oxygen for 152 millimeters, about 1% water, about 10 millimeters, and then some additional gases noted on this for a total barometric pressure of 760 millimeters of mercury. To calculate the partial pressure, as I've said, you multiply the barometric pressure times the concentration of the gas expressed as a fraction. So room air has 21% oxygen. Barometric pressure is 760. 760 times 0.21 is 160 millimeters of mercury. If the expired Desflurane is 6% in the alveolus, then the partial pressure in the alveolus is 760 times 0.06, or 47 millimeters of mercury. Conversely, to calculate the concentration, volume per volume, it equals the partial pressure of the vapor divided by the partial pressure of barometric pressure times 100. For example, if the Untitled carbon dioxide is 40 millimeters of mercury, the concentration of CO2 in the alveolus is 40 over 760 times 100, or 5.3%. Next, we wish to talk about flowmeters, and in general we use these in two regards. One is to measure the gas flows into the circuit, and the second for measuring tidal and minute ventilation into the patient. For gas flow into the circuit, in the past we routinely used flow tubes, but more and more modern machines are using electronic flow meters. The gas flow tubes are also known as variable orifice area flow tubes, or Thorpe tubes. They are mounted vertically and are tapered, i.e. they become wider as you move upwards. They contain two types of floats, either a bobbin, in which case you read the flow rate at the top of the bobbin, or a ball, in which you read the flow rate in the middle of the ball. Each of these tube meters are specific for each particular gas. And because they are made out of glass, there is some risk of damage resulting in leaks in the low pressure system. They employ the principle of constant pressure. The pressure gradient of gas flow around the float, i.e. between the float and the inside of the tube, exactly balances the weight of the float. As flow of gas increases, the velocity of flow increases, as does the gradient, which causes the float to rise. The float continues to rise until the pressure of the float is exactly balanced by the pressure gradient across it. Thus, the flow is proportional to how high the float rises. This illustrates the principle here. So we have the bobbin, which has a certain weight, and we have flow coming up from below, and as it goes around the narrowing between the bobbin and the tube, there's a pressure gradient, and this pressure gradient, when things are stable, exactly balances the weight of the tube. As the flow increases, the pressure gradient increases, and therefore the pressure gradient increases, and the bobbin moves up until it stabilizes at the new circumstance. Here is another illustration of these tapered tubes. And finally, yet another example of how the tube rises as the flow goes up. At low flow, the pressure gradient is small, but as the flow increases, the pressure gradient increases until the bobbin rises and the flow space is sufficient to match the mass of the tube. I have a missing slide here to indicate that, excuse me, here it is. Modern machines use electronic flow sensors, and at least 3 different varieties are made. One are hot wire anemometers, differential pressure transducers, and mass flow sensors. I had a picture of a mass flow sensor out of Miller's textbook, but it seems to have been lost in this slide set. One form of mass flow sensor has passes the gas through a chamber, and this is heated, and as the flow increases, more of the heat is removed, and the monitor measures how much heat it has to add to keep the temperature stable, and from this it can calculate the flow of the gas through the flow meter. We also use flow meters to measure tidal volumes out of our circuits. Most of these measure flow rates in milliliters per second, and by integrating flow rates over time, it can calculate the breath, milliliters per breath, and by multiplying that by respiratory rate, calculate minute flow. There are many different varieties of flow meters that are used, including the rotating vane, of which there are several varieties. The so-called Venturi tube, and as you recall, when flow goes from a wide orifice to a narrower orifice, the side pressure decreases, and based on the drop in pressure, it can calculate the flow. This is a so-called pitot tube, which measures the side pressure, compares the side pressure with the end pressure to calculate flow. This is a so-called Burden tube flow meter, which is used on high pressure flow systems, such as measuring the flow out of an oxygen tank. Basically, what this does is measure the pressure proximal to a narrow orifice. As the flow goes up, the pressure proximal to the orifice goes up, and this causes the tube inside this meter to expand, and hence the indicator shows higher and higher flow. And this is another vane spirometer. Another method is measuring the pressure difference across a wire mesh, which produces a slight resistance to flow. And this is an example of a flash flow meter, which includes a heater so that the orifices don't clog up as the flow is going through it. And finally, this is the pitot tube system, which measures differential pressure towards the pressure tube and away from the pressure tube, and can use to calculate tidal volumes. So now let's turn to the topic of vaporizers. The principle is that volatile agents are liquid at room temperature, and at equilibrium there is always some vapor in the atmosphere above the liquid. The amount of vapor is dependent on the vapor pressure, which is determined by the agent and the temperature. So the concentration of the vapor equals the vapor pressure divided by the total barometric pressure. And of course, the vapor pressure itself depends on the temperature. This shows the vapor pressure for the commonly referenced anesthetic agents at 20 degrees centigrade. For isoflurane, the vapor pressure is 238, for SIVO 157, and for Desflurane 664. Assuming a barometric pressure of 760, this shows that the concentration of vapor above isoflurane is 31%, above SIVO is 21%, and above Desflurane is 87%. There are at least 4 types of vaporizers which you may encounter. There is a conventional variable bypass vaporizers known as the Tec 4, 5, and 7, and the NA Draeger 19N and 20N. There's the Desflurane Dual Gas Blender, Tec 6, the Datex-Ohmeda Aladin Cassette, and the Maquette 950 series injectors. The Tec vaporizers for sevoflurane and isoflurane are referred to as variable bypass, flow over wick, temperature compensated, agent specific, out of system vaporizers. And this diagram illustrates these vaporizers. Fresh gas flow comes in through the inlet, and there is a bypass route which allows some of this gas to go through the vaporizer chamber, where above the liquid the gas is fully saturated, depending, as we mentioned before, the vapor pressure of the agent and the temperature. The device that adjusts the concentration of agent accomplishes this by producing gradual increased resistance, forcing more and more of the fresh gas flow to first go through the vaporizing chamber before it comes back. By knowing the concentration of the vapor in the bypass chamber and the flow rate, it can determine how much what the concentration of the output will be. So if the concentration of isoflurane here is 30%, and you want it to be 1%, it will mix 1 part of flow here to 30 parts bypassing this circuit, so that you end up with 1% isoflurane. If you want 2% isoflurane, you then cause twice as much gas to go through the vaporizing chamber to produce 2%. These vaporizers cannot work very well with Desflurane because of the high concentration of Desflurane would require very high bypass flows to bring it down to anesthetizing concentrations. It also results in a greater loss of heat, and this results in excessive cooling of the chamber. And thus they had to design an entirely new and different type of vaporizer. What they came up with was a so-called electrically heated, thermostatically controlled, constant temperature, pressurized, electromechanically coupled, dual circuit gas vaporizer. By dual chamber, it means there is two flows of the gas, two separate circuits. One is the fresh gas flow, and the other is a circuit from the Desflurane chamber. The Desflurane chamber is heated to 39 degrees, which produces a vapor pressure of around 1,300 millimeters of mercury. So here you have the fresh gas flow coming through. The machine monitors how much this fresh gas flow is based on the pressure gradient. And down below is the vaporizer chamber. This contains only Desflurane, and above it is 100% saturated Desflurane at, as I said, around 1,400 millimeters of mercury. Based on the known flow here, this machine automatically adds enough of this highly saturated Desflurane to the fresh gas flow to produce the desired concentration. More details about this are present in the wiki version of this podcast. In addition, this new vaporizer has a number of additional safety features, including it will automatically turn off if there's a low Desflurane liquid level, if it's tilted, if there's a power failure, and if the pressures in the chambers are not appropriate. When this happens, an alarm sounds and warns you that the device is not working properly. The third type of vaporizer is the Datex-Ohmeda Aladin Cassette vaporizer. This is similar to the first flow over vaporizer that we talked about before. So you have the fresh gas flow coming in, and some of this is diverted through the vaporizing chamber to produce the desired concentration of the agent. What is unique about this is that it is controlled by a computer which measures the flow rates and the temperatures and the type of gas and adjusts these flow meters so that it generates the concentration that you desire. Again, the computer then receives the data about the fresh gas flow, the type of anesthetic being vaporized, the pressure and temperatures, and the desired concentration, and based on this data, adjusts the outlet valves so that it generates the percent saturation that you request. The last one is the Maquette 950, which is simply a fuel injector type of device. And what it does is squirt the appropriate amount of vapor into the fresh gas flow to produce the desired concentration. This is a non-rebreathing system and was commonly used in the past with our cheaper anesthetic, but of course is impractical with the expensive agents that we use right now. There are a number of hazards associated with vaporizers, which are summarized on this list. And there are a number of factors that influence the output of vaporizers. One is temperature. The higher the temperature, the higher the vapor pressure, and hence an increase in percent output. But as indicated, these modern vaporizers are temperature compensated. Interestingly, fresh gas flow only affects vaporizer output at extremes, i.e. flows of less than 1/4 of a liter per minute or greater than 10 liters per minute. Interestingly, the carrier gas does influence somewhat the output, and at low flows, the Desflurane output is reduced by about 20% when using nitrous oxide. The pumping effect refers to the effect of back pressure due to positive pressure ventilation, but most modern vaporizers have check valves to prevent this from happening. Obviously, if you tip or tilt over the vaporizer, the liquid anesthetic can get into the upper portions and cause a massive overdose. There's also problems if you fill the vaporizer with the wrong liquid. And finally, we'll briefly comment on the effect of altitude. If you put an agent with a higher vapor pressure in a vaporizer designed for an agent with a lower vapor pressure, you will get a false high concentration. In other words, if you put isoflurane with a vapor pressure of 245 in a sevoflurane vaporizer designed for a vapor pressure of 175, you will get a excessively high concentration of isoflurane, and vice versa. If you put an agent with a lower vapor pressure in a vaporizer designed for an agent with a higher vapor pressure, you'll get a false low concentration. Finally, what about the effect of altitude on the output of vaporizers? This has little practical significance in your daily practice, but it does challenge you to understand exactly how these vaporizers work. Vaporizers are all calibrated at sea level. Regardless of altitude, variable bypass vaporizers, in other words, those for isoflurane and sevoflurane, put out a constant partial pressure of the agent. At a 1 max setting for isoflurane, 1.2%, this generates a partial pressure of about 9.1 millimeters of mercury. At this same dial setting, with increasing altitude and hence decreasing atmospheric pressure, it will generate the same partial pressure, in other words, 9 millimeters of mercury. However, the concentration expressed as volumes percent will increase. At about 6,000 feet, the barometric pressure is about 600 millimeters of mercury, and hence the concentration of isoflurane will be about 1.5%, which is 9 divided by 600. However, remember that the anesthetic effect is dependent on the partial pressure, not on the concentration, and hence the depth of anesthesia will be the same, even though the percent concentration coming out of the vaporizer will be higher. That is because the partial pressure will be nominal. On the other hand, the Desflurane vaporizer puts out a constant concentration of the agent. At a 1 max setting of Desflurane, in other words 6%, this generates a partial pressure of 6% of 760, or 45.6 millimeters of mercury. At this same dial setting, with increased altitude and hence decreasing atmospheric pressure, it will generate the same concentration, i.e. 6%. But the partial pressure will decrease. At about 6,000 feet, the barometric is 600 millimeters of mercury, and hence the partial pressure of Desflurane will be 6% of 600, or about 36 millimeters of mercury. Since the anesthetic effect is dependent on the partial pressure, the depth of anesthetic will decline unless one increases the dial setting. In summary, with the Desflurane vaporizer, the output is a constant fraction, and if the dial is set at 6%, it will put out the same concentration, but the partial pressure will be lower, and hence a less Mach equivalent. With other Tec vaporizers, the output is a constant pressure for a given dial setting, but the fraction will be elevated, but the anesthetic effect will be the same. Now let us turn to anesthetic ventilators, and I will discuss the types and the impact of changing fresh gas flow and a couple other issues. There are many ways to classify ventilators: by the type of reservoir, by the power source, by the drive mechanism, by the modes of ventilating or cycling, and if it's a bellows ventilator, whether it's a descending bellows or an ascending bellows. This is an illustration of the three main types of ventilators, the so-called ascending bellows, descending bellows, and piston variety. The term ascending refers to what happens to the bellows during exhalation. With the ascending bellows during exhalation, the bellows goes up. With the descending bellows during exhalation, the bellows go down. The opposite is true with, I think I misspoke. With the ascending bellows, during inspiration, the bellows goes up, and during exhalation, the bellows goes up, and during inspiration, the bellows goes down. With the descending bellows, during exhalation, the bellows descends, and during inspiration, the bellows ascend. These are irrelevant regarding the piston ventilator. During inspiration, the piston decreases the volume in the ventilator, and with expiration, the piston increases the volume. These are some pictures showing the so-called ascending bellows, which is what we commonly use right now, descending bellows, and a piston ventilator. Again, a picture of ascending bellows and descending bellows, which are rarely used anymore. Bellows ventilators are referred to as double circuits. They are pneumatically driven. It has a bellows in a box, a so-called double circuit. The bellows serves as a reservoir for the patient's breathing gas, like the breathing bag when you're not on the ventilator. The bellows is squeezed by pressurized gas delivered to the space in the box surrounding the bellows. The delivery of the pressurized gas, which drives or squeezes the bag, is under electronic control. The bellow refills passively during patient exhalation. Once filled, any excess gas is vented to the scavenger system. I've already discussed the difference between ascending versus descending bellows. Early in my career, most of the bellows ventilators had descending bellows. This was considered hazardous, and we converted to ascending bellows. However, there are now some safer descending bellows which are being used and manufactured in some machines. This discusses the safety issues surrounding the use of ascending bellows versus descending bellows. Piston ventilators are mechanically driven by computer-controlled stepper motors. The advantages is they don't consume gas, and they deliver a very accurate tidal volume. The disadvantages are that they are usually hidden, and so you can't visually observe their movement. They are relatively silent, and they will refill even with total disconnect, and can thus entrain room air if you have a surface leak. This is just a diagram of how the piston ventilators work. From the outside, you can't see anything about it. If you take it apart, you can see the components. Finally, there is another type of ventilator made by Cassette, which is called the flow-eye system, or a volume reflector ventilator. This is an unusual system in our country. I think it's used more commonly in Europe. It's very complicated to understand, and if you wish to pursue it, I recommend you refer to the chapter in Miller or the more extensive discussion in my wiki copy of my PowerPoint. Now, a topic that comes up, at least in the past, is what is the effect of fresh gas flow on the tidal volume that a patient receives. This was an issue with the older conventional Bellows ventilators. This is because the system is closed during inspiration, and therefore any fresh gas flow that enters the circuit during inspiration is added to the tidal volume. And so the tidal volume is not only the volume delivered by the ventilator, but also by any additional volume added by the fresh gas flow. How much is added depends on the duration of inspiration and the fresh gas flow. And the relative impact on the patient depends on the patient's size. So if you have a high fresh gas flow and a small patient, changing the fresh gas flow can make a dramatic change in the tidal volume the patient is delivering. In summary, with these old conventional bellows ventilators, the tidal volume will change if you change the fresh gas flow. If you lower the fresh gas flow, the tidal volume will go down, and if you raise the fresh gas flow, the tidal volume will go up. This slide here explains in diagrammatic detail how this occurs. For example, if the fresh gas flow is 5 liters a minute and the I to E is 1 to 2, then 1/3 of the time is inspiration and 1/3 of the fresh gas flow is added, or about 1.7 liters per minute. If the respiratory rate is 10, then 160 cc's is added to each tidal breath. Now, there are two strategies that have been developed by companies to prevent this problem. One is to monitor the exhaled tidal volume and adjust the tidal volume delivered by the ventilator to match the desired volume. The second is use of what's called decoupling. As I mentioned, many of them monitor the tidal volume and adjust the amount being delivered by the ventilator to correct for the fresh gas flow. However, this takes a few breaths for the machine to figure it out. And so if you watch the tidal volume while you suddenly change the fresh gas flow, you will see that for a few breaths, if you decrease the fresh gas flow, the tidal volume will go down, and if you increase the fresh gas flow, the tidal volume will go up until the machine has time to compensate for this error. The other approach is so-called decoupling, and what this does is divert the fresh gas flow away from the patient's circuit during inhalation, and it typically diverts it into the breathing bag. And this is illustrated in this cartoon. There are a number of potential problems with bellows and ventilators. If it's descending, it can fill even if there's a complete leak. If there are leaks, it can dilute the anesthetic and alter the FiO2. If the ventilator relief valve is open, you lose volume, and if it's closed, you can have barotrauma. And finally, if you have electrical failure, it can interfere with the drive mechanism or the controller. The latest models do have some adjustable inspiratory pressure limits to avoid barotrauma. Finally, let me say a few words about manual resuscitators, or so-called manual ventilators. This is well described in Dorsch and Dorsch, and more recently by this chapter in the MGH textbooks. Basically, these may be used during spontaneous or supported ventilation. They are used as rescue when the anesthesia machine has failed or you've lost gases to the anesthesia machine. They're also, as you know, commonly used while transporting patients. There are basically three components of these manual ventilators. There's a self-filling refilling bag, the non-rebreathing valves, and the oxygen air/oxygen reservoir. This is a schematic presentation of these manual ventilators showing these three components. This is a self-inflating bag, which you can squeeze to ventilate the patient, or the patient can inspire gases out of. This is the valve, which prevents rebreathing, and this is the oxygen reservoir. Oxygen inlet is added to the system here. And here are a couple of pictures of a couple different varieties of these manual breathing bags. The first component, the self-refilling bag, acts as a reservoir. It may be compressed to ventilate the patient during inspiration, and it automatically recoils and refills during expiration. It can be made out of rubber or plastic, and nowadays they are usually latex free. The key component, one of the key components, is the non-rebreathing valves. These ensure that exhaled gas enters the atmosphere and does not go back into the self-refilling bag. It also ensures that the patient receives gas from the self-refilling bag during either spontaneous or assisted ventilation. This rebreathing bag is T-shaped with three ports: the inspiratory port coming from the self-refilling bag, the expiratory port, which goes to the atmosphere, and the third port, which goes to the patient. A PEEP valve can be attached to the expiratory port to provide positive and expiratory pressure. Three different types of valves are used in these non-rebreathing systems: the so-called spring valve, the duck bill, and the flap valve. The third component is the oxygen air inlet oxygen reservoir. It may be either a bag or a length of large bore tubing. Oxygen enters the system at the opposite end of the non-rebreathing bag, and two security valves must be present to prevent excessive positive pressure or negative pressure in the self-refilling bag. For further details and pictures of these various types of valves, I refer you to my PowerPoint on Wiki. Having said this, it's important to realize that the function of these can be unpredictable and varies from device to device. They vary in how much tidal volume you can deliver. They vary in what the inspired oxygen may be, which is influenced by both the patient's minute ventilation and the fresh gas flow and the satisfactory function of the valves. They may vary regarding the amount of rebreathing, and they may vary in regard to the amount of resistance, especially during spontaneous ventilation and during expiration. Therefore, you need to review the manual for each of these devices. And that completes my podcast for the second part.